I had a grade school teacher who taught geography by pulling a map of the world down in front of the blackboard. I had a classmate in the 6th grade who raised his hand and he pointed to the outline of the east coast of South America and he pointed to the west coast of Africa and he asked, "Did they ever fit together?" And the teacher said, "Of course not. That's the most ridiculous thing I've ever heard." That student went on to become a drug addict and a ne'er-do-well. The teacher went on to become science advisor in the current administration. But you know, the teacher was actually reflecting the conclusion of the scientific establishment of that time. Continents are so big, obviously, they don't move. But actually, as we now know, they did move. They moved apart from one another, but at one time they did, in fact, fit together. But that assumption was a problem. It reflected the well-known wisdom that what gets us into trouble is not what we don't know, it's what we know for sure that just ain't so.
Hello, this is ramapascala. Yes, if you know me in real life, that's not my real name. What can I say? I'd planned on staying anonymous with this project, but recent events, which I'm going to talk about in a minute, have left me in a state of mind where I'm now just thinking, fuck it, I don't care who sees me on this anymore. So, this is a video version of the blog post that I wrote on my Substack, A Blog for the Anthropocene, which, if you haven't already guessed, is about climate change! Yes, good old climate change. Climate change is one of those things you hear about in the news, isn't it? You'll turn on the news one day and there'll be an item about Brexit, there'll be an item about coronavirus, there might be a piece about the Middle East, and then there'll be a piece on climate change. Usually it'll be world leaders signing a document or some protest of some form or another. And you'll watch and you'll think to yourself, oh yeah, climate change, that's important. We need to do more on climate change. We're not doing enough on climate change. You'll think this to yourself, maybe share a graphic on your Instagram, and then you'll go on about your merry day.
I never understood wind, and I know windmills very much.
I've started this project for two reasons. The first is that I do not think people fully grasp how bad the situation is, and sure, upon hearing that, you might have thought, okay, I get it, it's worse than I thought. Seriously, please just watch this and let me spell out to you how bad it is, because there are some key figures that I'm going to share in this video which are not in the public domain enough and are not being spoken about enough. The second reason is to share actual concrete solutions to beating climate change. Whenever you hear about climate change, the message is always, we need to do something and we need to do more about climate change. What something and more actually looks like is never spoken about enough, even by people you see in the media a lot like Extinction Rebellion and Greta Thunberg's crowd.
How dare you!
With this project, I hope to outline what the real tangible solutions to climate change are, what the implications of them are, and, crucially, how drastic the impact they'll have on our lives will be. And, as I said in the blog post, I'm doing this because I don't see this being spoken about enough, and it's frankly been eating me alive for the best part of 4 years now. Climate change is in the news a lot, but they don't tell you the key figures I'm going to show you here. They don't tell you what we actually need to do to fix it. And I still feel like banging my head against a brick wall every time I see climate change discussed in mainstream media. I don't know who's going to watch this. I don't know if this is going to gain any traction at all. But I have to make this. I simply have to. I can't stay quiet on this any longer.
Well, you can't grow concrete.
You can.
I'm not an expert, but I don't think I need to be. I did a degree in mechanical engineering and aerospace, and now I work in project management. I'm not an expert. All I am is someone who's read a lot about climate change, understands the full implications of climate breakdown, and can see clearly what we actually need to do to mitigate it. Hint, it's a lot more than switching to a Prius. There's a lot to cover, so let's get started. Climate change. We discovered fossil fuels, we burn them to produce energy, combusting them causes carbon emissions, carbon goes into the atmosphere, the greenhouse effect traps more latent heat, the earth warms up, yada yada yada. We all know this by now. If you take issue with the above sentence, then this video isn't for you. Go watch something else. Moving swiftly on. Tipping points. You may have heard about this. Mainstream media are actually starting to cover this a bit more nowadays. Across the world, there are many major environmental systems, for example the Greenland ice sheet, the jet stream, and the Great Barrier Reef. Here's a map of them. There are three main types: cryogenic entities, which is ice sheets and permafrost, cold stuff basically; circulation patterns, jet streams and monsoons, stuff that moves basically; and biosphere components such as the rainforests and the coral reefs, stuff that lives. All of these systems have specific ranges that they can operate within. If the Earth's climate alters, they will react and adjust their structure accordingly. This is the Daisy World model. It's a model used to demonstrate the ranges within which an environmental system can operate and, crucially, stabilize itself. Imagine a perfectly spherical planet with no oceans, no mountains, and a completely flat, you know what I mean, surface. Now imagine the planet is entirely covered with two types of plants, light and dark daisies. The light daisies reflect most solar energy, the dark daisies absorb most solar energy, and the daisies can grow between 5 degrees and 40 degrees. Below 5 degrees, it's too cold and the daisies can't grow. At 5 degrees, dark daisies begin to grow. Only the dark daisies grow here because they're the more absorbent ones. The light daisies reflect too much solar energy to survive here. The planet thus becomes covered in dark daisies. As the solar energy hitting the planet increases, light daisies begin to grow. This graph shows how the two daisy types change their coverage as the solar energy increases. At the lower limit of 5 degrees, it's entirely dark daisies, but as the solar energy increases, light daisies emerge, increasing in numbers until they reach a crossover point and overtake the dark daisies. This trend continues until the upper limit of 40 degrees is reached, at which point the planet is entirely covered in light daisies. Beyond 40 degrees, there's too much solar energy for even the more reflective light daisies to grow, and they die.
This idea that CO2 is a pollutant is pernicious nonsense. It's food for plants.
This graph is the critical part though. While the light and dark daisies continually change in numbers as the solar energy varies, the overall temperature remains the same. This is because the daisies work in harmony as an environmental system. While the daisies can grow between 5 degrees and 40 degrees, their optimum growing temperature is around 23 degrees, as you can see here. Therefore, as soon as the temperature of the planet is within range of the daisies, they begin to grow and rapidly bring the temperature to the optimum, and from here the system works in harmony to maintain that temperature by adjusting the ratio of dark to light daisies in accordance with the level of solar energy hitting the planet. Still with me? The system has limits. Below 5 degrees and above 40 degrees, the system has reached its extremities of solar energy. No daisies can grow in any capacity, and they die off in a rapid fashion. The system collapses. It's reached its tipping point. This lecture from the Center for Complexity Science in Mexico City explains this in much greater detail. I highly recommend you watch it. So, let's go back to this map. You guessed where I'm going with this yet? Every one of these environmental systems, to varying degrees, is a daisy world. They all adapt to varying levels of solar energy, but they all have limits. As an example, let's look at the Greenland ice sheet. If it receives more solar energy, it melts more and shrinks. If it receives less solar energy, it freezes more and grows. However, the ice sheet is very thick, well over 2 kilometers thick, and at some points over 3 kilometers thick, which means that the ice sheet's surface is at a high enough altitude that the air is naturally colder due to the lower air pressure. This means that if the ice sheet melts too much, the surface will sink to a low enough altitude that the air is too warm for it to grow back. From here, the warmer air will cause the ice sheet to melt more, which in turn causes the surface altitude to sink more, which brings it to warmer air still, which causes it to melt more, until all of a sudden you've got yourself a feedback loop. In order for the ice sheet to begin freezing again and grow back to its original size, the entire planet would have to cool down to a degree such that the air at this new lower down altitude is as cold as it was at the previous higher altitude. This is referred to as the ice elevation feedback.
You know what this is? It's a snowball.
This graph shows the feedback trend. The dark blue line shows the ice melting down gradually until the surface altitude reaches its tipping point and melts down rapidly. The lighter green line shows the much lower level of solar energy required for the ice to then subsequently grow back. However, notice that this is also a feedback loop, whereas the ice sheet grows to a higher altitude, the colder air causes it to freeze more, causing more growth. Another example, the Amazon rainforest. The tipping point here arises from the fact that the rainfall in the Amazon does not simply go through the precipitation-evaporation cycle that you learn about in primary school. The complex vegetation in the Amazon means that most rainfall goes through transpiration, where the plants absorb the rain through their roots and the moisture travels through their plant structure before evaporating off of the plant's leaf surfaces. What's more is that once the moisture evaporates, it won't simply move on in a cloud, but it will return back to the rainforest and transpire again, where it's in effect recycled. The moisture will be recycled as many as 5 or 6 times before finally moving on, and only with this moisture recycling can the density of vegetation be supported. This highly regenerative process is reliant on the Amazon being of a critical mass to support itself. Hence, you don't see this process in your own back garden. It can only happen on a large scale in a biosphere macro entity. The tipping point here very simply comes from deforestation, where once the size of the rainforest is reduced beyond a certain point, it becomes too small to support this recycling system, and the rainforest enters a period of rapid dieback as the system collapses. Without the regenerative moisture recycling system being present, the rainforest system will revert to a savanna system.
Because you know the earth is warming up, isn't it?
I don't want to get too bogged down in tipping points here, because as you can see from the map, these are just two of several. Moving on. This is Professor Will Steffen. He was a councillor on the Climate Council of Australia and the executive director of the ANU Climate Change Institute, and I say was because he tragically died of pancreatic cancer at the end of January. This is one of the main reasons why I've made this video. With prominent voices like Will Steffen no longer with us, I feel I have to say something. So here we are. Anyway. Steffen's work has focused on combining all of these environmental systems on Earth into one holistic model, the Earth system. In this model, a tipping point being breached will further encourage other tipping points to breach, creating a domino effect or a cascade. This is Steffen's focus, the cascade. Remember how I said that every environmental system was a daisy world? This cascade is like a daisy world collapsing, which then causes another daisy world to collapse, and so on. It's easy to visualize how all the systems are connected. A melting ice cap will expose the dark sea water underneath it, which absorbs more sunlight, which warms the ocean up, which causes more coral reef bleaching. A rainforest is cut down, which reduces its capability as a carbon sink, which causes the atmosphere to heat up, which causes more melting of the ice cap. They all have different sensitivities, and some are tipped far more easily than others, but they're all interlinked. This map shows the temperature sensitivity of each tipping point and how the tipping points are all interconnected. The yellow tipping points will be breached first, which then causes the orange ones to breach, and then ultimately the red ones.
This whole global warming thing is a total fairy tale.
Now, briefly, let's go back 2.4 billion years. Planet Earth has historically existed in two states, greenhouse and icehouse. Simply put, icehouse states were cold enough for glaciers and ice caps to form, and greenhouse states weren't. This graph shows the previous 2.4 billion years of the Earth's temperature out of the total 4.6 billion years that the Earth has been around for. The first 2.2 billion years, known as the Hadean and Archean eons, were mostly just asteroids smashing into the planet and supervolcanoes erupting, so we won't worry about them just now. The last 2.4 billion years, known as the Proterozoic and Phanerozoic eons, are where we've seen this fluctuating pattern of greenhouse and icehouse states emerge, as you can see. There have been 5 known icehouse states. The one we're in now is called the Late Cenozoic Ice Age. Let's zoom in. The icehouse state can further be divided up into 2 periods, glacial and interglacial. Again, very simple. Glacial periods are the cold bits, think woolly mammoths, and interglacial periods are the warmer bits in between. We're currently in an interglacial period, but not just because of climate change, we're there anyway. This graph shows the recent temperature cycles between the glacial and interglacial periods. You see this tiny wiggly bit hovering just above the center line here? That's the Holocene, and that's everything that's ever happened in recorded human history. From inventing the wheel to landing on the moon, from the pyramids being built to the launch of the iPhone, and from the Bible being written to Will Smith slapping Chris Rock in the face at the Academy Awards. All of it. Here's how carbon in the atmosphere varies with the glacial cycles. You'll notice this graph pretty much matches this graph. As carbon goes up, temperature goes up, and as carbon goes down, temperature goes down. The glacial and interglacial periods become pretty distinct and easy to identify, and throughout the icehouse state, the Earth has naturally oscillated between these two periods. Here's where it gets bad. Pay attention to the vertical scale here. That's carbon parts per million. You've probably heard that before. It's one of the key figures that newsreaders like to throw at you when they're talking about this. The average on this graph is around 240 parts per million. The glacial periods go as low as 200 parts per million, and the interglacial periods reach as high as 300 parts per million. Let's zoom in again. This graph may look more familiar. It shows the temperature range throughout the Holocene, which is considered modern humanity from when we invented agriculture to present. I don't need to point out the glaring red javelin pole at the end of this graph. You've probably seen a graph like this 100 times already. It's often referred to as the hockey stick due to the abrupt spike at the end, so let's look at carbon emissions shown here. Remember this nice carbon graph that peaked at 300 parts per million? We're currently well over 400 parts per million, and this is still skyrocketing. And I can't stress enough how mental this is. The last time Earth saw 400 parts per million was 4 million years ago, which was when the Earth was still cooling down from its last greenhouse state. So does that mean that we're reverting to a greenhouse state? No.
Good for you.
The problem arises from the fact that over these geological timescales, Earth's temperature and carbon have gone up and down in tandem. The two variables have decreased and increased harmoniously, whereas with man-made climate change, we have forced the carbon content up artificially, and Earth's temperature has gone up in reaction to this.
I don't even think it's clear that carbon dioxide is actually a problem, but
you have to understand that the 150 years in which humans have been emitting carbon is an unbelievably short period of time. Even in terms of human history, it isn't much. By the time we started emitting carbon to the point of warming the atmosphere, we already had video cameras, we already had light bulbs, we already had internal combustion engines. In terms of geological timescales, it's a tiny fraction of a second. Look at these graphs. Hundreds of thousands, millions, billions of years. 150 years is nothing. For reference, the Holocene, the current interglacial period, is over 11,000 years long. The extreme magnitude and speed at which the atmosphere has altered in the last 150 years has prompted many scientists to separate this time from the Holocene, terming it the Anthropocene, the period in which the atmosphere has been affected by humans. The extreme speed at which carbon has gone up in the last 150 years presents an incredibly dangerous instability in Earth's atmosphere, which has been visualized here. This graphic shows how the Earth naturally cycles between glacial and interglacial periods during an icehouse Earth. However, the stability of this oscillation is reliant on all the major environmental systems functioning properly and coexisting. Once these systems start to collapse, the cascade begins, and we very quickly enter extreme instability, as you can see here. So you can see how the Earth switches between glacial and interglacial states of stability. Once we go beyond an interglacial period, this happens. What these graphics visualize is what happens if all the tipping points are breached, the feedback loops escalate, and ultimately the Earth system is tipped. This rapid and unstable transition is not in any way akin to what a transition back to a greenhouse Earth state would look like, which would have taken millions of years. As a result, the Earth will transition into what many scientists have termed a hothouse Earth state. And this is different from a greenhouse Earth state. Previous greenhouse Earth states had all sorts of mad things in them, like palm trees growing in Antarctica. Hothouse Earth will have none of this, because it's essentially an icehouse Earth where all the environmental systems have collapsed. And that's not a good thing. Now for the really scary bit. What does a hothouse Earth state look like? To put it bluntly, bad. Very, very bad. Let's not beat around the bush and dive right into this, shall we? Extreme weather events. We've seen some of this already. Wildfires in Australia, abnormal flooding in Pakistan, drought in southwest North America. Seriously, get used to this. I want to take you back to the 2019 Australian bushfire season, which is now chillingly referred to as Black Summer there, and remind you of how apocalyptic a time that was.
People don't really understand it until you actually see it coming at you in a wall of flame.
Victoria declared a state of disaster, the first in its history.
A wall of fire and smoke blocking the path. As many as 4,000 people now trapped on the foreshore of the encircled seaside town of Malakuta.
This morning in parts of Australia, thousands fleeing as more than 200 fires rage in two of Australia's most populated states.
Seriously, when this happened in 2019, I couldn't believe that this wasn't the kick up the backside that the world needed because of climate change. This was apocalyptic. I cannot believe that no major action on climate change took place because of this.
You're not welcome, you fuckwit!
Environmental disasters of this scale are only going to become more and more frequent, and the associated disruption that they present to modern society is only going to result in more and more lost homes, lost livelihoods, and lost lives as time goes on.
Tell the Prime Minister to go and get from Nelligan.
Rising sea levels. Yeah? Remember all that stuff they told you about in primary school? It's going to happen in real life. They weren't just telling you that for a laugh. I needn't spend much time dwelling on this one, and shall let this map speak for itself. Every highlighted city here represents an urban agglomeration of over 10 million people, and all of the shaded areas are going to be underwater in a hothouse Earth. They are. This is going to happen. Soon. In your lifetime, if you're under the age of 50.
Hey, if we're underwater, how could there be a...
Uninhabitable climates. Here's the real kicker. Huge swathes of planet Earth are going to become totally uninhabitable for humans. As in, literally too hot for our bodies to regulate temperature without being in air conditioning all day. This is Professor Stephen C. Sherwood. He's a professor at the University of New South Wales' Climate Change Research Centre. And this is Professor Matthew Huber, who's a professor at the Purdue Climate Change Research Centre. In 2010, they published this landmark scientific paper. It's called An Adaptability Limit to Climate Change Due to Heat Stress. And to this day, it remains one of the most cited and most influential scientific papers published on climate change in the past 2 decades. What they did was they tried to find the upper limit at which human bodies can survive in a hothouse Earth. A brief reminder on how the human body works. Our bodies generate heat. We take in energy and we convert energy, and some of that energy is generated as heat. We generate heat at a rate of about 100 watts, hence the plot to the Matrix, plus any additional heat we absorb from external sources like the sun. This heat has to go somewhere, which is why we sweat, which is called evaporative cooling, and why we seek shelter from the heat when it becomes too hot, which is conductive cooling. Our core body temperature is 37 degrees Celsius, our skin temperature is 35 degrees Celsius, and you probably already know that these are pretty sensitive numbers. Any deviation away from these numbers and our bodies start to quickly malfunction.
And over 25,000 BTUs of body heat.
Evaporative and conductive cooling can only happen when the surrounding wet bulb temperature is lower than these temperatures. And to understand wet bulb temperature, you need to think about the temperature of an object when it's been set up to be at maximum heat loss, covered in water and with air blowing over it. So you can have the core temperature of an object, but without changing the surrounding air temperature, it can still be cooled down. You can cover it in water and that'll cool it down, and you can blow air over it and that'll cool it down. So wet bulb temperature refers to a temperature of an object when it's been cooled down as much as possible without actually adjusting the surrounding air temperature. This means that in a sustained wet bulb temperature of over 35 degrees Celsius, our bodies cannot regulate temperature and will overheat, inducing hyperthermia. Ah, I hear you say, but temperatures over 35 degrees happen all the time, all over the world. As the paper states, and again I highly recommend you read it, it's actually very rare for a wet bulb temperature of over 30 degrees to be observed anywhere in the world. Even in places like Saudi Arabia and Qatar, where temperatures regularly reach ridiculous levels of over 45 degrees Celsius, the wet bulb temperature never reaches this height because it's a dry heat. In wet bulb conditions, this temperature would drop significantly.
This is coal. Don't be afraid. Don't be scared.
Here you can see the global temperature distributions from 1998 to 2008. There are two graphs here because the data originates from two different models. I've included both for the sake of information. The blue lines are the maximum temperatures, where you can see the temperatures going into the 40s and approaching 50 degrees. The black lines are the 2-meter temperatures, which are irrelevant. And the red lines are the critical maximum wet bulb temperatures. Immediately, you'll see that the wet bulb temperature almost never goes above 30, no matter how hot the actual maximum temperature is. The vertical dashed line at 35 degrees Celsius represents the upper limit at which human bodies can regulate body temperature in wet bulb conditions. And here you can see the map of these two models, where you can see it usually ranges between 20 and 25 degrees Celsius. It never goes above 30, no matter how hot the actual maximum temperature is.
You're concerned if you're in the really hot region of Africa, but in terms of the United States and most of Europe, we're in pretty good shape. We're all blue.
Now let's look at a hothouse Earth model. At 4 degrees, over half of the world's population will be brought to within 1 degree of the upper wet bulb limit of 35. At 5 degrees, the upper limit is breached in some locations, and at 8 degrees, the upper limit will become the average wet bulb temperature worldwide. Here you can see the graph of this model, where you can see the dashed line at 35 has been breached, and here's the map. In anything above 35 degrees Celsius, humans cannot survive. We will die. Seriously, pause and look at this map. Where do you live? Where do you live on this map? Are you in a safe zone or not? Anywhere above 35 degrees Celsius is a death zone.
There's people that are dying.
So, that's a list of bad things that are going to happen, but what does all this ultimately lead to? Well, the most stark and direct way of measuring this is through a metric called Earth's human carrying capacity. How many humans are able to survive on Earth at any one time? You may have heard about this in mainstream media before, when Earth's rising population has been discussed and if there's an upper limit to it.
Now we have an underpopulation problem.
As you can imagine, it's a very difficult thing to accurately measure and model. Earth is a very big, very complex place with an awful lot of people on it after all, so scientific estimates have varied wildly from anything between less than 2 billion to over 1 trillion. These estimates also vary hugely depending on what level of resource consumption and living standard the models use, but the vast bulk of estimates range between 8 and 16 billion. However, the crucial point here is that these models use Earth's atmospheric conditions as they historically stood in the Holocene, an interglacial period in an icehouse Earth state, not the Anthropocene. Again, I have to stress, the Anthropocene is an astronomically short period of time in the grand scheme of things, so it's become even more difficult to accurately model things like Earth's human carrying capacity when the Earth's atmospheric conditions are changing so incredibly quickly. But scientists have given it their best shot.
The real nature of climate change, difference between a 2-degree world and a 4-degree world. 2 degrees doesn't sound like much, does it?
In attempts to model the Earth's human carrying capacity, where the Earth system is tipped and we transition into a hothouse Earth state, many scientific estimates place the Earth's human carrying capacity at around 0.5 to 1 billion. 0.5 billion. I'm sure I don't need to tell most of you this, but in case you need reminding, the current population of planet Earth has just hit 8 billion, and that's still going up. Ah, I hear you say, but that can't possibly be correct. Not convinced? Here's what various leading climate scientists have to say about it. Professor John Schellnhuber, Director Emeritus of the Potsdam Institute for Climate Impact Research and the former chair of the German Advisory Council on Global Change. In a very cynical way, it's a triumph for science, because at last we have stabilised something, namely the estimates for the carrying capacity of the planet, namely below 1 billion people. Professor Kevin Anderson, former director of the Tyndall Centre for Climate Change Research and the head of Energy and Climate Change at the University of Manchester. If you've got a population of 9 billion by 2050 and you hit 4 degrees, 5 degrees or 6 degrees, you might have 500 million people surviving. Professor William E. Rees, Professor Emeritus of the University of British Columbia and a Fellow of the Post-Carbon Institute. The long-term human carrying capacity of Earth, after ecosystems have recovered from the current plague, is probably 1 to 3 billion, depending on the technology and material standards of living. Professor Johan Rockström, director of the Potsdam Institute for Climate Impact Research and the chief scientist of Conservation International. It's difficult to see how we could accommodate 8 billion people, or even half of that. Professor Martin Scheffer, head of aquatic ecology at the Wageningen University and Research Centre, 1 to 3 billion people are projected to be left outside the climate conditions that have served humanity well for over the last 6,000 years. The late Dr. James Lovelock, a fellow of the Royal Society and the guy who invented the Daisy World model, in his own words.
I would guess, living the way we do, not more than 1 billion, probably less. It's largely a matter of how
you say that with
live.
equanimity, but that's postulating the most dramatic and terrible and unimaginable sort of cull of the human species.
Well, I'm stick by it. I think it will happen. I think it's very probable.
What time frame?
It'll take almost a miracle to stop it happening. This century.
This century?
Are you getting this yet? 0.5 billion. That's what's at stake here. Why this isn't on the front page of every newspaper every day of the week, I have no idea. And again, I have to stress, this isn't a what-if scenario or a worst-case scenario. This is what we are currently on course for. Unless we radically and fundamentally take extreme action to get the climate under control, this is going to happen. This will happen. In the words of Will Steffen,
maximum carrying capacity of humans. This is a difficult thing to calculate. A lot of argument and uncertainty, but a lot of scientists are saying about 1 billion may be able to live in a 4-degree world toward the poles. Our current population is about 7.5 billion. So you can do the sums. This isn't a nice future. And this is not going to be a gentle, planned population decline.
People are going to die. In their millions, if not billions. And seriously, if you're still sitting there thinking, that can't be right, listen to yourself. This is what leading climate scientists are saying. This isn't my opinion. I'm just parroting what leading climate scientists are saying. These are experts in their fields, and this is what they're saying. If you're still denying this, your argument has basically become,
well, you can prove anything with facts, can't you?
I hear you say, but how do people actually die from climate change? This is a fair comment, because whenever people hear the phrase dying because of climate change, they usually picture something from the day after tomorrow involving a giant tsunami, killing everyone instantaneously, or something else as equally stupid. It's not quite as dramatic as that. The reality is a lot more mundane and bleak. As an analogy, look at Ukraine right now. An active war zone where at the time of writing over 6 million people have fled. Ukraine is very unlivable at the moment and its population has declined in some part because of people dying directly in the war, but mostly because of people fleeing. This is what's going to happen in a hothouse Earth. Some people are going to die directly due to fires and floods and stuff, but most people are going to flee. Climate refugees are going to become one of the next great crises in the world, and this will affect every continent. If you take a look back at this map, you can see that large parts of South America, Saharan Africa, the Arabian Peninsula, India, Eastern North America, and Australia, the final two of which will probably receive by far the most attention because they're full of white people who speak English, are all going to become uninhabitable, and people will flee these places. And when people are fleeing a war or something similar, they do not breed. Dying is perhaps a misnomer then for the incoming population reduction, but through a combination of people dying and people simply not breeding due to crises and inhospitable conditions, the population will collapse, potentially to as low as 0.5 billion. And all this, by the way, is without even mentioning crops and food supply, but that's a whole beast in itself and for another video.
Claims that the reef is dead due to a natural atmospheric trace gas are a lie.
And here's the real kicker. Once we transition to a hothouse Earth state, there is no going back. To demonstrate the permanence of this, we're going to go all the way back to part 2 and look at the tipping point of the Greenland ice sheet shown here. To jog your memory, the ice sheet melts down gradually until the feedback loop kicks in, causing a rapid collapse. In order to grow back, the temperature at the much lower down altitude of the collapsed system would need to be as low as it was at the surface altitude of the ice sheet pre-collapse, meaning the entire Earth would have to cool down enough to accommodate this. This is why the up curve, representing the ice sheet freezing and growing back, is at a lower value of solar energy than the down curve, representing the melting and system collapse. Now go all the way back to the beginning of this video, look at this map, and remember that this is the case for every environmental system tipping point. Now combine them all into the Earth system and imagine its tipping point. This tipping point has actually been modelled on a long-term scale over the next 10,000 years. If you go back to these two graphs which show the rapid spikes in CO2 and temperature, the following model shows what happens if these spikes continue and the Earth system is tipped. This is the next 10,000 years of a hothouse Earth. This is the single most important graph in the world at this moment in time. This graph should be on the front page of every newspaper every day of the week and should be the first thing shown on the news every day on TV. There is nothing on Earth which is more important than this graph. This is a permanent change which cannot be undone. And seriously, if you're gonna call me a doommonger or an alarmist or accuse me of catastrophizing, then what I would say to you is it catastrophizing if this is a genuine catastrophe? Because this is a genuine catastrophe. This deserves this level of discourse.
I'm not gonna panic over the possible increase in global temperature of, at maximum, 4 degrees Celsius.
And I'm not trying to be a doommonger. I'm not trying to catastrophize with this. This shit keeps me up at night. This is genuinely how I feel about this. And seriously, anyone who knows me in real life can attest to this. I'm not a hippie. I'm not a tree hugger. I'm not a member of any environmental activism group. All I am is someone who's seen the data. I've seen the data, and this is what's at stake, and no one is realizing this. No one gets this. People think about climate change, and they think about it as, yeah, it's bad, and it's gonna get worse, and we need to do something about it. But people don't realize the reduction of the human carrying capacity that's gonna happen. They don't realize the permanence of it, and they don't realize that it's not a linear thing where it'll just get worse and worse and worse. It's a cliff edge, and we're currently in the process of going over the cliff. So finally, to tie this all up, let's go back to the here and the now. What is the current status of all this, and how long do we have to prevent it?
Vegan sausage rolls.
The Earth system has not been tipped yet, but we're currently tipping it. It's in the process of being tipped right now, and you've probably gathered from this video, we're already at the stage where some of the damage is irreversible. We're already in the damage control phase of climate change. We can prevent a full transition to a hothouse Earth and prevent many of the tipping points from being breached, but some of the damage has already been done. The Arctic sea ice, the general consensus is we've already tipped that one. The Great Barrier Reef, that one's being tipped right now. You remember the Paris Agreement in 2016? The one that Trump famously pulled out of? Ha! That target was 1.5 degrees Celsius. We've already blown that.
The citizens of Pittsburgh, not Paris.
The bottom line is, we need to get carbon down to zero very, very quickly. The latest any scientists are advising for getting to net zero is 2050. Many are saying 2040, and nowadays more and more are saying that if we don't get to 2030 carbon net zero, we'll have passed the point of no return. If we do pass the point of no return, we'll have flipped into a hothouse Earth state by 2100. Things will start to get really, really bad around 2050, and from there we'll see the anticipated population collapse. This graph shows the difficulty and speed at which this needs to be done. Bearing in mind that emissions are still going up, yes, despite everything you hear about net zero carbon nowadays, emissions are still skyrocketing. The later we leave it to bring emissions down, the steeper a decline it has to be and the harder it becomes. So yeah, 2030. That's in 7 years. 2 World Cups away. You'll also notice that this graph is hilariously out of date now, showing the paths that we could have taken in 2016 and 2020, which we've already blown. This now leaves us with the steepest 2025 path to bring carbon emissions down to zero by 2030, maybe 2040 at the very latest. But given what's at stake here, Is that a risk we're really willing to take? To conclude, if we do not get carbon emissions down to zero within the next decade, we are going to permanently flip the Earth from its current icehouse state to a hothouse state, which could have a human carrying capacity as low as 0.5 billion. Take a moment to pause and let this sink in. We are currently sleepwalking towards our demise as a species. So the next time you get angry at a bunch of Extinction Rebellion members who have smashed up a bank, or some Insulate Britain members who have blocked a road, take a minute to realise that unless they start killing billions of people, what they're doing isn't as bad as what they're protesting against. Zoom out and look at the bigger picture. This is one of the general problems with climate change discourse. Everything is still being spoken about on too small a scale. We're still seeing Piers Morgan trying to nail activists with stupid gotcha questions like, do you own a TV? We're still being encouraged to do inane baby steps things like Meatless Mondays. We're still being told to not print emails to save the planet. Who prints emails anyway? And we're still being told how eco-friendly our offices are for installing hand dryers instead of paper towels. Zoom out. We need fundamental, structural, institutional changes which are implemented top-down, not bottom-up, by world governments. We need global changes. And unless we do this in the required time frame, which is not getting any longer, we're doomed to a hothouse Earth and a population collapse. And with that, I bring this to a close.
The assumption is something like this. The Earth is so big, we can't possibly have any lasting harmful impact on the Earth's environment. And maybe that was true at one time, but it's not anymore. And one of the reasons it's not true anymore is that the most vulnerable part of the Earth's ecological system is the atmosphere.
So, if any of this has scared the living shit out of you or made you profoundly depressed, join the club. Yeah, that's it. That's it. I'll spare you the spiel that I wrote in the blog post about how down the rabbit hole I went with this and how depressed this made me, but in short, it leaves you feeling very disillusioned with the world around you once you realise how bad this shit is. Especially if you live in somewhere like the UK, a first world country like this. You just find yourself watching the news and thinking, none of this matters. None of the other problems that are in the news right now matter with this looming over us. It makes you call into question the way governments work, the way we consume things, everything about the material world that we've set up around us. It's all fundamentally at odds with this. And having kids... The idea of having kids now, knowing the world that we're bringing them into, it gives me the fear. It really does.
Task Force Leader, cannon, knife up. You guys headed out yet?
As I said on the blog post, this is by far the biggest problem that Earth faces. And I hate to do this, and I hate to compare it to other issues, but it utterly dwarfs anything else we've got going on. Corruption, pandemics, poverty, even wars, none of this shit will matter if we're all dead. I cannot say this in more blunt terms. This shit is going to kill us if we do not fix this. This shit, can I be any more clear than that? This shit is going to kill us. If I'm to offer you a small crumb of comfort, there are solutions to this, but they're not pretty. They need to be enacted right fucking now, and they result in your life getting worse in a comparable way to how it got worse during COVID-19. And no one in mainstream media is willing to admit this, nor do I even think our most prominent voices in climate activism, which is why I'm making this. And if you want to see what these solutions actually look like, check out my blog where I've started writing up the solutions we need to be implementing if we want to avert this. And stay tuned to this channel because I plan to make these into further videos as well. This is crisis management. We're past the point of transitioning into some rosy utopian carbon neutral future. We're putting out a fire. We need to be treating this like a national emergency, like a pandemic or a war. That's the way we need to be approaching this, and the strategies with which we do this are what I'm outlining with this project. Check out the blog and stay tuned to this channel for more videos. And if we don't do this, the alternative, 0.5 billion. And it's permanent.